the expert DL talk presented by our guest speaker. Um, for the brief introduction, I would like to request our chapter advisor, Dr. Pankaj Sharma, sir, to give some introduction about our chapter.
Thank you,
Sir.
Sachidanand. Thank you for organizing this distinguished lecture talk. Once again, I take this opportunity to welcome Professor Abhishek Dikshit from IIT Delhi to consider our request for delivering the invited distinguished lecturer. Thank you, sir. We at IIIT Jabalpur are from Advanced Semiconductor Materials and Research Group. We have recently started this IEEE Electronic Device Society Student Branch chapter, recently inaugurated on 27th of January by Professor Navakant Bhatt from IIC Bangalore. And we have made a plan that every month we'll be organizing one distinguished lecture series. So I'm really happy to inform you that, sir, this is the first invited distinguished lecture in this series, and there could be no more better option for us, for our students, to hear from you on this occasion, sir. So I'm really happy that you are sharing your research work. You would be presenting the advanced domain of cryogenic, CMOS, and quantum computing, sir. Once again, I welcome you for distinguished lecture, sir. Thank you, sir.
Thank you. Thank you.
I request Sachidanand and Rajiv to please provide a brief introduction of our distinguished lecture.
Thank you, sir. Dr. Abhishek Dikshit obtained PhD in Electrical Engineering from KU Leuven IMEC, Belgium in 2007. From 2007 to 2013, he was with IBM SRDC as an advisory research engineer and worked on characterization and compact modeling of various CMOS technology for server and value-based foundry products. He joined Indian Institute of Technology, Delhi in 2013, where he is currently a professor of electrical engineering holding the NXP Phillips Chair of Microelectronics and VLSI Design. His research interests include modeling and characterization of silicon-based qubits and CMOS devices at cryogenic temperature and reliability of RF CMOS devices and circuits. He has 6 US patents and more than 100 co-authored publications in international conferences and journals. He is an IEEE-EDS Distinguished Lecturer, Senior Member of IEEE, Editor of IEEE Transactions on Device and Materials Reliability, and Fellow of IET UK, IETE, and IEI. Now I welcome our guest speaker, Professor Abhishek Dikshit, on behalf of IEEE-EDS Student Branch Chapter, IIIT-DM Jabalpur. We are really obliged that you accepted our invitation. Thank you, and now over to you, sir.
Okay. Thank you, students. Thank you, Dr. Pankaj. Thanks for inviting me and giving me this opportunity to be able to talk to you. So before we start, how much time do I have for the lecture?
So we have scheduled the lecture limit for 1 hour. Maybe you can wrap up by 5 and then 5-10 minutes question answer sessions.
Okay, so let's try to finish by 5. So I'll just keep the lecture around 45 minutes if possible. Okay.
Okay, sir.
All right. So my timer.
One request before
Yes.
before you start,
Yeah.
sir. All the students, if you have the bandwidth available, so please I request you to turn on your cameras since it's an online event.
No, my
We need
camera
to
is on. Can't you see?
No, not sir, not for you. The participants I'm asking. Sorry, I'm really sorry.
Oh, okay.
Because we need to capture the pics for this event.
Yeah.
So I request those who can avail the bandwidth, please turn on your cameras. Thank you, sir. Please,
Yeah.
you may.
All right. Okay, so thank you and welcome to this distinguished lecture. It's my privilege to be giving the first distinguished lecture at your student branch. So the cryogenic CMOS modeling and characterization, we'll talk a little bit about what is happening in quantum computing applications area. Cryogenic CMOS is used for other things as well, but right now quantum computing is getting a lot of traction My voice is clear, right?
Yes.
Yeah, okay. So, and you are able to see my projection as well?
Yes, sir.
Okay. So,
Yes,
yeah.
sir.
So, let's move on. So, before we go further, I'd like to draw the attention of the students towards the IEEE Electron Devices Society. The EDS, basically the motto of Electron Device Society is to promote excellence in the field of electron devices for the benefit of humanity, and largely it has been very successful in doing so. EDS, as we all know, Electron Devices Society, covers very broad range of spectrum of research, so many different kinds of devices, technologies, products that EDS takes in. So it's a very large society within IEEE, and has been in existence for a very long time, and it has been very successful in doing what it intends to do. As I said, EDS is very diverse. These are some of the fields of interest of EDS. So basically all aspects of engineering, physics, experiments, simulations, so all kinds of research work on electron and ion devices, even materials, insulators, metals, plasma. So many things is all falling within the EDS domain of interest. Of course, there is a lot of direct benefit of EDS membership to the students. Currently, I saw for this year that up to some time the EDS student membership was for free. So if you are a IEEE member, a student member, you can take EDS membership for free, and there are range of benefits of joining EDS as a student member. So if you haven't already joined EDS as a student member, I request you to consider joining this. You can go to the website IEEE.org/EDS and try to see for yourself what is the opportunities that EDS offers to the students. With that, I reach the outline of my talk. So let us try starting with a motivation slide and talk about what is CMOS, what is qubits, and then we can do more about the cryogenic CMOS operation and compact models. I will try not to go into too many details at this stage. Details will come later. We'll see how we are doing with respect to time, and accordingly we'll decide whether to how deep to go. So quantum computers are not everywhere like the laptops, mobile phones and desktops are. So they are not that present everywhere. But quantum computers are everywhere in the news. Okay, so a lot of people are talking about quantum computers, and the purpose of quantum computers is to achieve quantum supremacy. When we talk about quantum computers, in general, when people talk about quantum computing, they are talking about quantum communications, where there's a lot of security and defense related discussion on things like cryptography and talking about the RSA tokens and so on. So that's quantum communications area. There is also a lot of talk about quantum computations, where the target is to make a general purpose quantum computer. That's the kind of area we are really focused in. Quantum communications work more falls in the range of photonics and other kinds of devices that are not, at least in my area of interest. So we limit ourselves to quantum computations, which basically means that we try to make a quantum computer which can demonstrate supremacy over a classical computer. Classical computer is what we are currently operating, right? So when you talk about quantum computers, the first thing you talk about is quantum bits. So as you know, bits are basic units of information in computers. So right now what you have are logic bits, zeros and ones. Similarly, in quantum computers you will have quantum bits, or abbreviated as qubits. So it's again the basic unit of information in quantum computers. Of course, these are extremely fragile. Fragile not in the sense of if it falls it breaks, not like that, but it's very fragile in terms of holding information. The information can get very easily corrupted, right? So it requires cryogenic temperature operation. Um, you need a circuitry to sort of control these qubits and read out the information written on the qubits. Circuitry, depending upon what qubit you are operating, could have RF, right? Could be just DC, could be even microwave pulses and things like that. And this kind of circuitry will operate between 233 Kelvin and 353 Kelvin. And interconnects, we'll talk about it in the coming slides. They will introduce thermal noise. Okay. So cryogenic CMOS, where it fits in, the cryogenic CMOS is what is used to make the control and readout circuitry for qubits. Okay, qubits can be made in multiple different ways. Those of you who are following the news articles will see there are qubits made up of single trapped ion inside silicon. There are qubits made up of neutral atoms. There are qubits made with photonic devices. So there are many various ways of making qubits. The most popular being the superconducting qubits, which is what, for instance, IBM and Google are using, and they have been able to demonstrate something like 128 qubit logical qubit quantum computer, right? So, and that number will keep going up. Whereas the second popular qubit technology is actually the semiconducting qubits, which is where my research focus is, which is closer to CMOS. And so in these qubits, you can do co-integration of this readout circuitry CMOS, control circuitry CMOS, and qubits to reduce, basically get various advantages like power consumption, reduced complexity, right? So we'll see this going forward. Let's little bit talk about basics. What is cryogenic temperature? I have just captured some things of the internet. You can see minimum and maximum temperature recorded at the surface of Earth, right? Moon, Mars, outer space, and for reference I have given the liquid helium and liquid nitrogen temperature, right? So you can see normally outer space is where the coldest temperatures are encountered. Also certain poles of moon will also have very low temperatures. So currently the game is about liquid helium temperature 4.2 Kelvin, which is where all your this kind of readout circuitry operates, right? So that now you understand what is cryogenic temperature. So before I get into this slide, we said that 2 slides ago we said that these are extremely fragile and they require cryogenic temperature operation. Why we said that? So if you take, for instance, some kind of a barrier, right, in a typical semiconductor device, and let's say it's a barrier for electrons. This is what happens, for instance, in the source channel junction of a MOSFET, right? Let's see if I should be able to draw with my mouse. So it will not be very clear, but I can still try. So you have this kind of a gate of a MOSFET. You have the source and you have the drain. So this is a source, let's say this is N plus. Channel of the device is p-type. So these electrons, when do they enter the channel? If all of you who have followed the basic MOSFET physics will know that electrons cannot enter the channel unless the barrier for electron injection is lowered. And how this barrier looks like? The barrier looks something like this, right? So your electrons in the source are here. They cannot climb this barrier. Now how much this barrier can be? This barrier will be basically few kT, above few kT. So kT over Q is the thermal voltage, 26 milli electron volt at room temperature, right? So now what is happening is, I'll write this value also. K is Boltzmann constant, T is the temperature, KT over Q. Room temperature value is 26 milli. Electron volts you can add. Okay. So now if the temperature is lowered, so what is happening is, if let's say I go to a higher temperature, I go to say 120 degree C temperature, right, degree Celsius, what will happen? This KT over Q number will increase because the temperature has increased. It will not be 26 millivolt, it will be actually much higher. So that much energy this electron has, it is basically vibrating somewhere here with that much energy. So the more energy it has, this is called the thermal energy, the more energy it has, the more likelihood is that although you have not lowered the barrier, the electron can actually cross the barrier. So in a way, electron is likely to cross a barrier if you sort of keep the thermal energy high. So how do you stop electron? Because this, see, the qubits we are making, we are talking about single electron effects. That's where the quantum phenomena will happen. So how do we stop this from happening? Let me draw something. So let's say you have some kind of a n plus region, okay, and I place a gate here, then I place another gate here, using this gate, let's call this as A gate. It's an accumulation gate. So this is p-type semiconductor. So if I bias it appropriately, there will be inversion layer here and these electrons can come here. Okay. Now depending upon how much is the potential here, I can allow certain electrons to come here. Okay. And let's call this as a depletion gate. So basically I can make a quantum dot here. Okay. Just by controlling the potential at A, I can allow a single electron to come from this N region and stay here. Okay. Similarly, I can have some kind of a plunger, and then I have another quantum dot. So again a dot. I can make a quantum dot here also. I can again have a electron here and again something like a accumulation gate and basically mirror symmetry on this side. Setting this plunger gate, I can actually have a single electron occupy this or this quantum dot. So this is what is called as a double quantum dot, DQD based qubit. So I have various situations, right? So based on this various situations, I can define what is state 0, what is state 1 for the qubit. And now the trick here is that once I have reached this single electron condition, and of course you need to lower this so that the electron is not, these electrons are not surmounting this barrier because of thermal energy. That's why you have to keep lowering down the temperature as much as possible. So we are now talking about something like 20 millikelvin, and you can see that 20 millikelvin is a temperature lower than anywhere in the universe, right? So it's a really low temperature. So at 20 millikelvin we assume that electrons will have no thermal energy. They will not surmount any barrier on their own because of the thermal energy. So wherever you allow them, they will go. So your control is very good on the potential. So as a result, if the electron is in the left qubit, let's say left quantum dot, I will say that this is in 0 state. if the electron is in right quantum dot, I will say that this is in one state. Okay, I hope this is clear this far. I'm trying to explain something little complex. So when now you think about basic quantum mechanics, we talk about superposition states, right? So basically we do some magic and we make a superposition of these two states. So while your logic qubit, you can say this is either 0 or 1. This is what we have understood in the second year BTech courses, that a logic bit can either be in state 0 or state 1, depending upon what is your assertion level. Could be positive logic, negative logic, but there is a 0 and there is a 1. No third state is allowed, right? Logic bit cannot be in any state other than a 0 or 1. If it gets stuck in some metastable state, the circuit will do something to bring it to one of these stable states. So this is basically a bistable multivibrator. So two stable states, 0 and 1. In case of qubits, once it is in superposition, you can take this state 0 and 1 and any linear combination of these two states. Okay. Now this gives you sort of a lot of time people explain it using a circle, right? And they say that it can take continuously any number of states. So basically this infinite possibility. So your qubit, once it is in superposition state, can be anywhere between a 0 and 1, and there is no limit really on how many states the qubit can stay, right? So that far we are clear. We need to cool it down, we need to put it in superposition, right? Now so what we have covered is why 20 millikelvin you require. Let's now try to cover, and then we have covered why you require superposition. Superposition. The third and last thing I want to, because a lot of students are attending this talk, I want to sort of stay at basics so that they benefit from the discussion. Last thing I want to talk about is the entanglement. Okay, I'm writing with a mouse, so I am very brief in writing. Somehow I should have actually taken it on the on my tablet, so it would be easier to write. But anyway, so entanglement. So now we know these qubits are maintained at very, very low cryogenic temperature. Any amount of thermal noise will corrupt the state information of the qubit, right? As I said, it can be anywhere between a 0 and 1. And once this information is lost, it cannot be recovered. I think many of you would remember, and those who don't remember or haven't gone through, you can read about quantum mechanics from Feynman lectures, famous thought experiment that Schrödinger did with the cat, right? The cat is dead and alive at the same time. So what those experiments, and even the double slit experiment, what those experiments say is that any quantum system, if you make an observation, you destroy the state. So whatever superposition state between 0 and 1 this qubit has, if I try to see whether it's in 0 or 1 or which state, the moment I try to see, I destroy the state. So the question is, how do I see? How do I measure what state the system is in? To do that, what we do is we sort of keep another similar qubit close to this, and because of the state of this qubit, the other qubit actually gets affected. And once the qubits are in such a situation where one is affecting the other, on a higher level, you can call them as entangled qubits. So you observe the entangled qubit and you don't disturb this qubit. So of course, when you observe the entangled qubit, you destroy the information in the entangled qubit, but the information in this qubit is going to stay on. Okay, so that's how at a very, very high level quantum computers are supposed to do the job, right? and you can sort of try to see basic information. If you have 2 logic bits in a digital system, 2 bits, you get 4 possible states that the system can take, that is 0 0 0 1 1 0 1 1, right? So 3 bits, if you again write, you will get to 8 states, so it's basically 2 to the power n, right? Whereas a quantum system of this kind of nature will exponentially scale, right? So with the 100 logical qubits, there are so many possibilities that the system can reach, right? So a lot of times people say it is 2 to the power 2 to the power n or something like this. There are various kind of explanations in quantum information theory, right, depending upon how you design your system. But basically, with same number of logical qubits, the quantum system can give you many more possible states of the system, and that's the reason why it is so much more powerful compared to a classical computer. Okay, so that's the quantum information sort of basic explanation to you. Now what we try to do is I'm trying to show you what is the current scenario in the lab. Our qubits are here. Let's switch back to the pointer. So our qubits are here. We keep them at 1020 millikelvin intermixing stage of the dilution refrigerator. Of course, reaching this kind of low temperature, it is very, very difficult. So the lower this temperature gets, the cooling capacity of this fridge is also very low. So at this stage, the cooling capacity is probably just 40-50 microwatts. Okay, you go to 4 Kelvin temperature stage, the cooling capacity of the system is more. You go to 77 and other higher temperature stages. So these are like different racks you can assume in the refrigerator. So since the cooling capacity is very limited, any wires that you bring from outside and connect to this stage to your qubits is going to cause extra thermal load in your system, and as a result, if this is overloaded, then it will not reach 10 millikelvin. It will never reach. It will probably saturate at a much higher value, so you will not be able to maintain the qubits at 10 millikelvin. Okay, so this is where your qubits are kept. This is where your control circuitry is kept, and this is where a lot of other things are utilized. Then there is a feed through which all the wires come into the dilution refrigerator. The instrument rack includes things like arbitrary waveform generators, microwave sources, digital to analog converters, oscilloscopes, digitizers, and range of instruments which are used to measure this kind of quantum systems. So what is very important for us is to make sure that not too many wires are here, right? So if I say that one qubit requires 10 connections, if I want to measure 2 qubits at the same time, I require 20 connections. If I want to measure 4 qubits at the same time, I require 40 connections. 40 connections is a lot of wires whose other end is actually connected somewhere in the room temperature. So it's going to bring in a lot of heat because these are metals or good conductors. So that's not possible. So what we do is we bring in few wires and we do multiplexing. What is multiplexing? You make one into many, right? So you can bring, let's say, 8 wires till 4K stage. At 4K stage, you design what is called as a cryo controller chip. Cryo controller chip will have on-chip multiplexers, which will multiplex between 4K and 10 millikelvin all the wiring you require, right? So this is kind of off-chip interconnection which is required. So not only qubits, you need to design something like cryo controller chip, which will have a lot of on-chip multiplexers and things like low noise amplifiers, right? Intel has a very good 3rd generation chip called Horse Ridge 3. That is their 3rd generation chip, probably launched within last 1 year. So they are using that for this purpose, but of course this is not a commercial chip. Intel is using it for their own quantum computer experiments, so we can't buy it. But those interested can see how to design a cryocontroller chip and what all components it has. Okay, so this is the current scenario, and noise, always remember, is a big killer here, right? Noise means increasing this, and then electrons will not listen to you. They will start jumping on their own, and your complete quantum system will break down. But just coming back to this, you can't really avoid noise as much as you want. So what will happen because of the noise, and not just thermal noise, there can be voltage noise, there can be many different kinds of noise. What this noise will do is it will corrupt, inevitably it will corrupt certain qubits in your system, and as a result you don't do computation with one qubit, right? If let's say you make 10 qubits, it is possible that if your system is not well designed, there is high amount of noise, maybe out of 10 qubits 6 qubits are corrupted and are giving you wrong information, 4 qubits are giving you correct information. So like this, you have to sort of characterize your system and get an idea of what kind of redundancy you need to put into your system. So you can, if you require, let's say 100 actual qubits, 100 logically correct qubits, you may have to design 1 million physical qubits, depending upon how much is your error rate. So error rate will be higher when the noise is higher, right? So it works like that. Since a lot of this development is in early stage, the error rates are very, very high. So people are already designing like hundreds of thousands of qubits to get to 100 or 200 good logical qubits. And every time we do a computation on this, we basically, since this is quantum mechanics, so we always look at the statistical expectation values of everything. So we always sample so many qubits and then look at the expectation value of the answer rather than answer in a particular qubit. So that's the way to work with this kind of a system. So now what we are proposing, that the previous slide was showing basically what is the status as of now. What we are trying to propose is that something like this. So we have a hardware division of a quantum computer. Of course there is middleware and software and whatnot. So all that we are not talking about, we are really looking at the quantum processing unit or processing unit CPU of a system. So here you will have something like a quantum data plane, right, where you have the qubits, which you will have to maintain, like I showed in the previous slide, around 10 millikelvin. You will have control and measurement plane, which is where your control circuitry is, right? So your control circuitry is going to be cryogenic CMOS, and then you will have the host processor plane. This is a known beast, right? This is your classical computer. So what you want really is, from a system point of view, is that we don't want your quantum processor or QPU to carry extra load. So all this, Ethernet and sound card and sound blaster and memory handling and all this stuff, you want the big guy to do, right? The old big guy to carry all that IO and that sort of a thing. What you really want is that this control plane really parses only very reduced instructions to this quantum processor, where actual ALU type computations are needed, right? And it will only do that part. It will not do all this other stuff which does not require those infinite states, right? If you talk about state machine design, I'm sure many of you EECS students would have done a state machine design in a second year course, finite state machines and so on. So then what we are proposing is, we are saying qubits are, so CMOS is anywhere there for control and measurement plane. Let's make qubits also out of CMOS, so that everything is CMOS in this part, in these two parts. So that's what we are calling a co-integrated design. It's a big thing, but since we are talking about millions of qubits, we don't know of any other technology than CMOS where you can make so many things so many complex things with very little variability and very high success rate. So hope is that if we try to do it this way, eventually we'll be able to make many large qubit systems and real quantum processors. University of New South Wales in Australia, Kavli Institute of Technology, Netherlands, Intel in the US. These are all the people who are trying to do similar things with CMOS and silicon type qubits. Okay. So that's kind of the green part is the kind of dream we are trying to follow. But this is, let me extend it a few more things. So this is not where it really ends. This is really a concept, and even if we are able to do this, I have sort of given a lot of undue credit to the good old processor by saying that it will do I/O and everything. But just think about it for a moment. If you are doing very complex computation, you will again at some point of time fall back to the concept of registers and cache memory and things like that. So you will at some point of the time, you will, whether you want or not, you will again be talking about this blue line you see, what kind of bandwidth is required here, how information flows from one into another, whether interconnects are good enough, on-chip interconnects are good enough, or you would want off-chip interconnects, whether you would want photonic off-chip interconnects. So once you think about a system like this, that's when you are in the real game. I mean, making a single device, making a single material layer is important for science, but very far away from the product. Once you think about a system at this level, that's when the real game starts. That's when industry gets interested in what you are doing as an academic. That's where industry gets highly interested in hiring you as a student, because your knowledge is something that can be easily translated into a real world product. Okay, so it's important to think about things for EECS people in this context. Okay, so very heavy motivation, but considering the large number of students in the audience, I think it was required. So cryogenic operation, we have already said that this is a low temperature operation. Then we start thinking that how CMOS behaves at cryogenic temperature. Traditionally, CMOS has been used minimum at minus 40 C, right, and maximum at plus, let's say, 180 C, which is again for your automobile application. So the chips which are now if you look at a modern car like a driverless car and so on, these have 400-500 ICs in one car, right? So all these ICs which are mounted on a car near the engine, so ECU for instance, engine control unit, is a major chip that every car has, and multiple of them in fact. So engine gets heated when the car is running, so this will reach this kind of 180 C temperature. So we have, based on the requirements, we have always looked at CMOS performance between these two temperature ranges, right? So the temperature range is minus 40 C to plus 180 C. And now we are going in a completely different domain. So what is minus 40 C? How much is that? So you just basically subtract from 273.40. This is 233 Kelvin. We are talking about 10 millikelvin and 4 Kelvin, right? So we have not looked at how CMOS behaves at these temperatures. We had the initial idea that these will show improved performance, again because of lower KT by Q. So turn on capabilities will be enhanced, mobility will be higher. Now specifically, since we already said any amount of heat is going to be very bad. If the devices do self-heating, it will be very bad for us. Then before we make a technology, we always do reliability. Although reliability is something which always degrades with higher temperature, and we are going towards lower temperatures. But unless we do it, so reliability is something that you have to do. There's no sort of empirical content in reliability. It all is about experiments. So we want to see what hot carrier degradation, time dependent dielectric breakdown, any bias temperature instability, what these do at cryogenic temperatures. Only once we kind of qualify this at 4 Kelvin, then we can say that yes, we can make cryo CMOS. So this is where this slide shows where last 2+ years my group has been really working. And then this is more about really details, right? Subthreshold swing, again KT by Q comes in there, so it saturates in a MOSFET at 60 millivolt per decade, right? If you go to lower temperatures, of course subthreshold swing will be lower, so your transistor will turn on faster. But if you look at the measured data, the models do not capture this, right? The Boltzmann limit, because you reach, so the models will not capture this. I'll show you some data there, right? And there are reasons, physics-based reasons, where people are talking about crystalline disorders, seeping of density of state, tail in band gap, right? So similarly, if you look at how the threshold voltage changes, various effects actually take threshold voltage in different directions. So if band gap widening is happening, your threshold voltage can go up. If incomplete ionization happens, threshold voltage can go down. All right. Effect of Fermi potential can take the threshold voltage up and then saturate. Interface traps can, increase the saturation value. So all of this happens, right? This is about mobility. So this typical room temperature mobility curve, right? So you have here, the Coulomb scattering, which is your ionized impurities scattering, and then you have the phonon scattering, which is sort of in the medium field region, and then high field you have surface roughness scattering. So this is the room temperature concept, right? And it is observed that Coulomb and surface roughness scattering dominate at low temperatures, right? Phonon scattering will be less, and the reason for that is a black body radiation type phenomena. This is about self-heating in these devices. So what self-heating can actually do? Since many students are here, I can explain. We are just looking at a bulk FinFET or any FET versus a SOI FinFET. So you see that some hot carriers are basically available here, and once there is a lot of current flowing in the device, lattice phonons are going to carry the heat, right? And heat can go in either direction, right? So it can go up, it can go laterally, it can go down. In the bulk devices, the heat can easily go down because the silicon substrate is a good thermal conductor, so heat can go down, can be easily extracted. As a result, your thermal resistance will be lower, right? Your lattice temperature will be lower. Okay. If you look at SOI, since there is a buried oxide thick layer here, which is bad conductor of heat, a lot of heat will not go down, right? It can either go laterally, and then you can think about in a dense layout there will be devices right next to it. So laterally also there is not much gradient, heat cannot flow much. So only thing it can do is it can go up through the gate and source drain contacts. So that results in a higher thermal resistance and a higher overall lattice temperature, which is what causes self-heating, right? And we know that this heat is bad, especially for the devices which have to operate at very low cryogenic temperatures. This is that phonon blackbody radiation thing I was talking about, right? So you are basically saying that at cryogenic temperature, phonon blackbody radiation is the key mechanism that allows thermal dissipation. So normally what happens, how the heat is carried, as I said, these highly energetic electrons are going to interact with the lattice, and lattice vibrations is basically what the phonons are, and these phonons will take the heat away. And how they will take the heat away? They basically collide with another lattice site, lose some energy, and like that they dissipate the energy. In this case, what is happening is Since the lattice is not vibrating, you are at a very very low temperature, so scattering is minimized of these phonons. So a phonon that gets generated can almost, without any scattering event, can exit the system. So that's why it says that it is almost like a black body radiation kind of analogy, because negligible scattering events are present at cryogenic temperature, right? So we say that each time a phonon is generated, it takes the heat away without any scattering. Okay, and it's a kind of something that has been analogically shown by people. But again, this is hypothesis. What is happening is what I explained to you here. How you can explain it based on the hypothesis, various people will present various hypotheses. So when self-heating happens, you can see, so it's kind of interesting slide. This is showing change in the temperature of the gate, okay? And this is the power which is causing the self-heating. So as the power will increase, the change in temperature will increase. Basically the gate will heat up, right? And you can see these contour colors, right? So 4.2 Kelvin is somewhere this dark blue color, right? You can see that this kind of delta Tg is highest for 4.2 Kelvin, whereas if you go to a higher temperature, let's say 300 Kelvin, then you can see this is, for the same power, it is just 10 Kelvin increase in the gate temperature, whereas at 4.2 Kelvin for the same power increase is like 50-60 Kelvin. So there is almost 40-50 Kelvin difference in the temperature rise between 4.2 and room temperature case, which is a cause of concern. So this is basically in a nutshell saying that lot more self-heating is happening when the ambient temperature is lower. Okay, so that's a good research area for students, PhDs and so on. Maybe a lot of in future a lot of TCAD can also be utilized to address some of this. Okay. So now I am kind of at the end of my time, and I have roughly a lot of material to cover. So what I'll do is I'll skip this part. So really a lot of quantum material I could not cover. Maybe some other talk I'll be able to cover that. Let me go to the summary slide and try to sort of summarize. Yeah. So what we have done in last two plus years is we have done how cryogenic CMOS performance is different from the room temperature CMOS performance, and this is all industry standard, production ready technologies from various integrated device manufacturers, foundries and so on. So we looked at these short channel devices, 10 nanometer, 7 nanometer and so on, CMOS, digital CMOS type devices. And then we looked at the industry standard compact models which are used for simulation of circuits by designers. BSIM CMG, for instance, is the industry standard model for FinFETs. So we compared the data measured at room temperature and at cryogenic temperature. We did the model simulation at both temperatures, and we realized that model was not really able to capture data because model did not have correct equations for the cryogenic temperature. So we did a lot of work in augmenting the existing BSIM CMG model and introducing our own Verilog based equations so that down to 4.2 Kelvin BSIM CMG can capture CMOS behavior. Okay, and this is done for threshold voltage, subthreshold swing, mobility, and basically wherever it was needed. I had shown in those papers about how this improved fit looks like. And reliability, some of the work we have done in TDDB area that was also published recently. we are currently doing some work in hot carrier degradation in cryogenic area, and then we are also working on the qubit side of the CMOS. So how to use a CMOS device as a qubit itself is where some work is going on. We are designing a lot of layouts, templates, and so on, so that we can get it partly fabricated by foundries, and then we can, measure our own circuits and devices. So that's all I wanted to cover today. Thank you, and let's have question and answers.
Thank you, sir. Now we are open for question and answer session of the talk. If anyone has any question, please ask.
Sir, am I audible?
Yes, yes.
Thank you for this wonderful talk, sir. So my question is, like when we consider the self-heating effect, then how we can find the best way to avoid the self-heating effect? Because now we are moving from FinFET to nanosheet. So as you mentioned that the cryogenic temperature has very less self-heating effect. So
No, I said at cryogenic temperature, self-heating effect is much more.
much.
So it has much less capacity to absorb self-heating. If little self-heating happens, then also the cryogenic system will not work.
So sir, any way to avoid this self-heating effect, or like we are researchers, so we can go in this area.
So,
This
well,
way.
reducing self-heating. See, self-heating is something that is. So I was talking about thermal resistance, right? So thermal resistance is something which has dependence on your layout, how the devices are, physical design is done, at what voltage are you operating the devices. So now, for instance, when we are talking about qubits, at present we don't really operate qubits in kind of saturation IDVD type biases, right? We are talking here, you are seeing 1 volt applied to the drain, 1 volt applied to the gate, and huge self-heating happening. Whereas when you are operating a qubit, you are probably biasing the gate at very moderate gate voltage and microvolt type drain bias, right? So it's likely that at those voltages, the self-heating is not as bad as you see that in context of a digital, inverter type MOS operation, right? Because your voltages will be very, very low. But we don't know. I mean, it depends really on how you design your quantum system. So, I mean, bringing it back to the point, self-heating is going to be a important design concern, right? If your system operates in the range of voltages where self-heating affects the system, then you have to do something to sort of reduce it. Otherwise, your quantum system will never work.
So, sir, here one more thing you mentioned that qubit terms, where you mentioned that in slide number 9, so many gates where we want our electron in the confinement regions. So, like I know MOSFET and I know FinFET and nanosheet. So for this depends on geometric structures. Then only we can get one type of dimension. I mean, one electron.
Yes, you're right. So confinement can be because of the potential barrier, and confinement can be because of geometry. So certain geometries are better to make single electron systems, like you are talking about nanosheets, right? It's highly geometrically confined, or fins, for instance. These are more apt for making these kind of single electron or few electron systems, as compared to planar bulk MOSFET, where structural confinement is very less, right? So these modern devices are better suited at this, and when we are making these kind of qubits, we are already pushing the boundary of even the 5-7 nanometer nodes and placing the gates much closer to each other. Okay, we are talking about 10 nanometer sort of 15 nanometer kind of gate pitch, which is not achievable by any optical lithography that is done now. We rely on things like electron beam lithography to realize that. Yeah.
Thank you, sir.
Yeah.
Excuse
Anyone
me, sir.
has question, please? Yes.
Yes, sir. Thank you for the lecture, sir. Actually, my doubt regarding to the capacitances with respect to the temperature, sir. So while we are sweeping the gate voltage till certain voltage, the capacitance are following some positive temperature coefficient. After that, the capacitance are following negative temperature coefficient with respect to temperature, sir. So,
No, which capacitance?
sir, that is gate capacitance, sir. CGG.
So you are saying that if you sweep from a cryogenic temperature up to the room temperature,
Yes, sir.
the TCC, right? You're talking
Yes,
about
sir.
temperature coefficient of capacitance,
Yes, sir.
right? So you are saying TCC becomes switches between negative and positive.
Yes, sir.
It's possible. Possible. I agree. Can do that.
So actually, so what can be the reason, sir? Because till certain voltage, it is following positive temperature coefficient from low to some middle of some around 0.5. After some 0.5 to 0.7, it is following negative temperature coefficient,
No.
sir.
So what is your source of this information?
Sorry, sir. So
No.
actually, the device is nanosheet FET, sir.
No.
And,
But this that you are saying this, is this a TCAT or some simulation based observation?
Yes, sir. Actually, that is a TCAT simulation data, sir.
Yeah. It all see TCAT results all depend on the model and calibration and things like that, right? So a
Yes,
lot
sir.
of times you see things in TCAD which may physically never happen. I'm not saying that this may not happen, but I'm just giving a general concept. So
Okay.
unless I see something happening on a measured piece of hardware, I do not really spend much time thinking about why this is happening,
Okay, sir.
right? So and this is a simple thing, right? You can anybody who has access to cryogenic setup can actually take a MOS capacitor and try to see if they are seeing a inflection in TCC with temperature, right?
Okay,
If they see that, then of course it is worth investigating why it is happening and what are the sort of consequences of that.
Okay, sir. Thank you, sir.
Yeah.
So, sir, here dilution refrigerator is used to generate the temperature, requirement temperature.
Yes.
So how we maintain the how we maintain the external temperature to internal temperature, because while we are measuring the experimental data, definitely the setup is out of the box of this refrigerator. So what technique we use?
No. So your device is in the refrigerator.
Device is in refrigerator. So the connection will come from the refrigerator to outside. So there is again temperature difference.
Gradient is there.
From
Yes.
room temperature to down. So if we measure the value from this metal wire, so suddenly the temperature changes for the metal.
Yeah. So
So,
what you
this
do
is
is once those wires come into a, let's say the wires come from outside into a 4 Kelvin stage, you cool the wires to 4 Kelvin first. So it's not just 4 Kelvin. Once they come in, you cool them at 100 Kelvin, then you cool them at 50 Kelvin, then you cool them at 4 Kelvin, then you take them to 20 millikelvin further. So you have to cool the wires, and not really the wires. We don't call it cooling the wires, we actually call it cooling the electrons.
Okay.
See, electrons, whatever energy they have is KT dependent, right?
Okay.
So they are carrying an energy which is dependent on the temperature that they are at. So you have to cool the electrons.
Yes.
Yeah.
Okay,
So
sir.
these are called bobbins. These are called thermal bobbins. So there are bobbins. Huh? is nothing but a large good conductor of heat, which is like a metal, large piece of metal, and your wire comes in and the current passes through that metal, which is cooled at a certain temperature. The thermal inertia of that, or let's say call it thermal capacitance of that metal, is much larger compared to whatever input load is coming in. So whatever passes through the wire takes the temperature of wire forward, right? That's the kind of thing it is.
Okay,
Right.
thank you.
So you can think about pouring boiling water, right, with a very less quantity, right? So you open a tap which has a boiling water flowing on a large slab of ice, right? So you can make a drain in the large slab of ice. So after the boiled water travels certain length in that drain of large slab of ice, the water actually acquires the temperature of the ice slab.
Ice.
It's no more boiling water. And then there is a tap and you collect that ice water at the other end. That's precisely what a thermal bobbin does.
But sir, again, it's a vice versa thing. Suppose I'm sitting in a room, so it may be a dilution refrigerator, and I want to measure the temperature at outside because my wire is going from this room to outside, my refrigerator to outside. So again, the temperature differences. So these type of things we have to take care.
Yeah. So those are taken care. That's what I'm saying. The people who sell dilution refrigerator, they have worked all this already out. Once you buy a dilution refrigerator, all this is there. You don't have to worry about it, because see, we are either electrical engineers or sort of computer engineers. We are not mechanical engineers. We can't do thermal design, right? So this is interesting because at a system level we have people from all material, mechanical, chemical, all kind of people working in this. It's not a one-man show. I mean, without a diverse team, you can't really make something like this possible. Okay?
Yes, sir. Thank you, sir.
All right.
Thank you very much, sir, for your very informative talk. I'm really thankful that you took time out of your busy schedule and shared the latest developments in cryogenic, CMOS technology, and quantum computing stuff. I'm sure that many more students are still having their questions. So I've circulated that email in the chat box that they can share their details and any questions they may have. So they may share with us because we have already passed the time limit. So one more question, if we may take any
Sure.
students, any student, if you one last question we are willing to take. Okay, if there is no more questions from the participants, one question as an advisor I would like to ask, sir. How can we collaborate in terms of IIIT and IIT-D in terms of like student transfers in this particular technology, and how we can get benefited from the research of IIT-D?
Okay. So basically, I am still presenting. I think you can see this thing, right? You are able to see my projection?
Yeah, we can see your screen, sir.
So everything that I am talking about, I have intentionally set up in this under this unit called Central Research Facility of IIT Delhi. Okay. So you can see what facilities are there. You can book those facilities on a charge basis. Okay. So you can see appointment slots, and you can see all kind of systems and all kind of labs. So this is my lab. Okay. And you can see there is a cryo prober setup, there is a DC noise setup, load pull setup, solar simulator. So you can book any of these setups. Anybody in India and abroad, industry, academics, can book this, pay for the usage, come here, and a TA will assist them in doing the measurement. So that's the kind of model I always wanted to make for this kind of work, so that anybody who has, let's say, a piece of silicon and they want to do cryogenic measurement or something, they can come and do it, right? So that's the way forward. So your students are welcome. We get students from so many different institutes coming year, and in future whenever dilution refrigerator is currently ordered, but it will take almost a year before it is delivered here. In future whenever dilution refrigerator comes, that setup will also be under this same umbrella, right? So that anybody can use it, because see, these equipment they cost tens of crores of rupees, right? It's not possible for all the institutes, and it is also not required to build redundancy, right? So in that way government is very supportive, and I think this is the right way forward. So please, if you have students who are interested in doing measurements and so on, you can encourage them to do this kind of CRF booking, and they can always come and do their measurement.
Okay, sir. Sure, sir. Thank you, sir. Thank you for sharing this with us. We will certainly provide the information to the students. And the problem is, like, at our end, we are very much limited to the theoretical stuff, only modeling stuff. We don't have any experimental setup as of now. Hopefully, when we have the
so see, this is also one thing. I mean, having experimental setup is still easier, right? Because you get a grant from a government sponsoring agency and you can create the setup. Getting the hardware is the problem, right? You can't fabricate. Who will give you the hardware?
Yes.
Right. So that's where the trouble is. That's why we don't want to create too many setups across the country, because we know the hardware is not there.
Yes, sir.
Right. So IIT Delhi, for instance, has the entire nano research facility. So many 100+ faculty members work there. They make their own devices, right? So they can always use all this setup.
Yes, sir.
So that's the bigger disability that we have in the country. Not having much of chip manufacturing and fabrication type thing, which now we are trying to address using India Semiconductor Mission under the leadership of the Honorable Prime Minister.
So what kind of support can we target towards the government for under this semiconductor mission, sir?
So currently we have a 100 faculty team which is doing very putting a lot of hard work, weekly meeting and so on. So right now we have roughly 100 faculty member team across all the IITs and ISC, which is trying to prepare sort of a mission summary and resource requirement and everything. The idea is we are in phase 1 right now. In phase 2 we will start including NITs and triple ITs and so on, so that we can expand it to more and more people. Yeah.
Yes, sir. So we'll certainly keep in touch, and I'll take this matter offline also with you.
Yeah, no issues.
Thank you, sir. Thank you very much once again for sharing your valuable time and valuable information. Thank you very much. So I hand over it to Sachidanand to propose vote of thanks.